Alright, so now we are going to be doing some real problems on testing a hypothesis about a population mean value, about a value for mu. So let's look on our computer screen here to start out with. Let's look at example 1. So on the computer screen here, example 1 says pulse rates generally have a known standard deviation of 4 BPM. And now part A of example 1. A sample of 74 people gives a mean pulse rate of 73.65 BPM. And by the way, BPM stands for beats per minute. At significance level 0.01 is our sample of pulse rates, showing strong evidence that generally pulse rate should be greater than 65 beats per minute. And so after viewing my video on general understanding regarding testing a hypothesis, then we understand that before we proceed into testing any hypothesis, we must, as our first responsibility, we must be able to identify the two hypotheses, the null hypothesis, H sub 0, and the alternative hypothesis, H sub 1. So now, again, back into my computer screen, the question is ultimately asking, is our sample of pulse rate, so this is our sample over here, sample of 74 people that gives a mean pulse rate of 73.65 beats per minute. So the question is asking, is this sample of pulse rate showing strong evidence that generally mean pulse rate, if we pay attention to this information right here, we want to prove that mean pulse rate should be greater than 65 beats per minute. So allow me to have a little bit of scratch work here, but mean pulse rate is symbolically notated by the mu symbol, and this is the population mean value for mean pulse rate. So we are trying to argue that mean pulse rate should be generally greater than 65 beats per minute, and we don't even need to write the actual units. And so this statement here is in the form of an inequality statement. So just right out from what we've learned through the general discussion, the general understanding regarding testing a hypothesis, then this statement can be used perfectly as a statement in our alternative hypothesis. So now as far as H1, we would have our statement saying mu is greater than 65. And in that way, again, learning from our general understanding regarding testing a hypothesis, then once we have found our alternative hypothesis H1, then finding H sub 0 now can be easily done by simply from where H1 is, we're just simply going to replace the inequality symbol with the equality symbol, and there we have for ourselves our null hypothesis. And so now null hypothesis says mu equals 65, and alternative hypothesis says mu is generally greater than 65. I'm now about to introduce a term that was not introduced back in our video lecture for general understanding regarding testing a hypothesis. But this type of testing, and allow me to give the full complete explanation at the end of this particular problem where I have successfully put all the steps together. But for now, this test, before we start the actual testing hypothesis, the statement in the alternative hypothesis here is saying that mu is greater than 65, and so notice how the inequality is pointing to the right hand side. And so the test we're about to use is going to be regarded as the right tail test. And so now, to actually get into testing our hypothesis here, the first step that we need to do is to identify our sample. And so back in the reading of our example problem right here, a sample of 74 people gives a mean pulse rate of 73.65 BPM. So this is our given sampling information right here. So we already had a sample mean value. So this is a sample mean value. So now first step is to indicate the sample value that we already had or being given. So X bar here in our case is being 73.65. And this sample that we are using is out of a sample size n equals 74. So that's our first step. We need to observe our sample. Either it's given or we have to find it ourselves sometimes. And now the next step, realize again that anytime we are collecting a sample or anytime we're picking up a sample at a whichever sample size, then we must clearly realize that our sample here is not the only sample ever existing out there. In fact, there are infinitely many other samples exist out there at the same sample size, 74 values on each. So knowing that fact, we understand that eventually we can have the center, the average of all sample means here. So our mean is, just remind yourself again, our mean is only one among many other sample mean values. And this mu x bar here is the population mean of all sample means where 74 is in each sample means. And so our mu x bar here, in our case here, I know mu x bar will be equal to 65. And allow me to give a detailed explanation, the detailed explanation of why and how I came up with this value mu x bar equals 65 at the very end after we have successfully put all the steps together. But so the impact right now, the role of this mu x bar is, once again, it is the center of all sample mean values. And then the next step here is to realize that since we're having so many sample mean values out there, they can be above or below this average of all sample means. And so standard deviation of all sample mean values, it's going to be 4 over square root of 74. So here I can throw in some little bit of explanation, but this 4 right here came out from our given information back on my screen. Even before we got into any of the example part A, B, and C, our example 1 has a general description. Pulse rates generally have a known standard deviation of 4 BPM. So this piece of information that I am highlighting right here is indicating that we are having a sigma value. So recall yourself the concept of sigma that we have learned before. So this value 4 right here is our sigma value, or in other words, we had a given sigma value being 4. And make note for ourselves that in this problem, our situation here, we have a given sigma value. Calculation comes out to be 0.46 in decimal. And depending on different applications out there, every problem will have a different requirements for how far in terms of how many decimals to round for sigma x bar. So watch out for those different requirements in different problems. But here throughout my entire video lecture here, I am going to be using 2 decimal places for all of my sigma x bar values. And so again, back in our current problem right here, sigma x bar in 2 decimal places is 0.46, which came out from 4 divided by square root of 74, the sample size. The next step now, once again, realizing that our sample mean that we're currently having is not the only sample mean that we're having. There are simply many other sample means out there. So particularly right at where our sample mean value that we already had, then our sample mean relative to this center of all other sample mean values right there, we have a z-score. So we are now going to calculate the z-score of our sample mean. And again, z-score anyone viewing this video is familiar with what a z-score and how to find a z-score. But optionally here I use a subscript x bar to indicate that this z-score is specially calculated for my current and for our current sample here. So z-score is from where our current sample value being 73.65. I am going to subtract 65, the center of all sample mean values data, and we're dividing that by sigma x bar, which is in this case 0.46. So we're putting 0.46 in the denominator. Calculation comes out to be 18.80. And unless being specified otherwise, usually I would go with 2 decimal places for any z-score calculation. So it would be the same here. So our z-score should be a positive 18.8. And now after finding out the z-score for our particular sample and being a z-score of positive 18.8, the next step would be setting up a probability calculation. I am going to find the probability that among all sample means. So recall that sample means as a random variable is being indicated by a capital X bar as a random variable name. And the sample mean here, since being at sample size 74, I am using a subscript 74. But X bar 74 here basically represents a sample mean. So here, as a probability problem that we're setting up, we're finding the probability where our sample mean goes anywhere greater than or equal to 73.65. So at this point, let's check for a couple of consistencies right here. So right here at our z-score step, we can use that as a checkpoint for consistency. Our alternative hypothesis is having a right-hand side inequality, meaning the inequality itself points to the right-hand side. So the z-score should be consistent with that in a sense that the z-score here is a positive z-score. And further, even though I did not explain what exactly the right tail test is, but having a z-score positive is also a checkpoint to check for consistency with the fact that our z-score is being positive, making it consistent with our test that we're currently following is a right tail test. And further, at this formulation of our probability setup point right here, using a right tail inequality right here is also consistent with the fact that our alternative hypothesis was pointing to the right, and our test here is decided to be used as a right tail test. And then the value that we're setting up in our probability problem is the value of our sample mean. This probability value, once we have found it, we will regard to that as the p-value of our sample. It's the p-value of our sample, and in this case our sample is a sample mean value. But now once we have successfully set it up, this probability calculation, then realize or imagine that on a bell curve that contains all sample means of size 74, then 73.65 as a sample mean is somewhere on the bell curve like this. And this inequality, this probability statement is asking us to find the area that is shaded to the right hand side on the bell curve and to the right hand side of 73.65. And so at this point, to actually calculate that probability, we understand that this probability is equal to the probability that on the standard normal distribution curve, we're looking for a z-score anywhere greater than or equal to 18.8. And this z-score came out from our previous calculation on the z-score of our particular sample. And so now we are going to start using our LS&D program that we have used throughout all calculation on the bell curve problems. And when we are asked for a z-score, we are going to provide 18.8 for the z-score. Since this problem is looking for the area shaded to the right-hand side, don't forget that we need to subtract the answer from the LS&D program from 1. And so now on my computer screen here, with my LS&D program currently running, 18.8 as a z-score will have an area to the left, completely shaded to the left on the standard normal distribution curve to be 1. So this answer here comes out being 1. But our p-value is calculated as 1 minus 1. Because this answer 1 is from the LS&D program, and we must subtract from 1. And so our final p-value is 0.0000. I am introducing a value 0.000 to indicate the fact that our final p-value is not a hard 0, but it is a value that's close enough so that even in 4 decimal places, it's still just 4 zeros here. But now, once we have found the p-value for our sample, one more time, let's look back at our question of the problem. The question is ultimately asking, is our sample of pose rates showing strong evidence? So what matters for us at this point, because so far p-value is only a calculation and we've been doing just steps and steps of calculation. But now once we have come to this p-value, then how can we go from here, from this p-value, to decide whether or not our sample here can be used as strong evidence? And so now in that way, with the significance level given in a problem being 0.01, that's our significance level that I just now wrote in red ink right there. The p-value must be compared with the significance level in order to decide whether or not we're having strong evidence or not. And so here in this case, the comparison comes out showing that our p-value is well below 0.01. It's just a comparison that came straight out from redoing our own calculation on the p-value, and the significance level was already given in a problem. And so now that is enough for us to say that at this point we decide that our sample is strong evidence. The sample mean that we're currently using is strong evidence. But strong evidence for what purpose? It is strong evidence. It is strong evidence to reject H sub 0, our hypothesis, our null hypothesis. Or we can say that our sample is strong evidence for us to support the alternative hypothesis, H1. And so ultimately, looking at the question itself, then the question is truly a yes or no question in the way how it's written. Is our sample of pose rate showing strong evidence? So the question is looking for being strong evidence, and it is a yes or no question. And now we have just decided that our sample that we're currently having is strong evidence. So in that way, the ultimate answer to this question must be a yes. Our sample of pose rate is showing strong evidence. Let's now look at the detailed explanation of the steps that were taken in example 1, part A. So we have already seen how to come up with the two hypotheses from the wording of the problem. So I am not going to go over again how the two hypotheses are being identified, but here instead I am going to give the explanations after we have already identified the two hypotheses. So here, just as a reminder, in our testing hypothesis problem of example 1, part A, then we were looking at a claim in the null hypothesis stating that the mean pulse rate of a human being is 65 beats per minute. And then the alternative hypothesis was stating that generally it should be the mean pulse rate should be greater than 65. And here I am not going to be too worried about whether this testing hypothesis problem is a left tail or a right tail or a two tail. We will get to all that explanation as we go along in this detailed explanation. But now, as far as the sample, after seeing the claim in the null hypothesis here, and again, and here I have to emphasize what's being stated in the null hypothesis here, the value being 65 here, before proving it to be truthful or must be rejected, then this value is a claim. So H0 or the null hypothesis always brings up a claim here, a claim about the population mean value. And here in this particular problem, we're studying about the population mean pulse rate. And again, back to the sample that I was talking about, then the sample we found here is indeed 73.65, and the sample was collected at sample size capital N equals 74. So this is our sample mean, and this is our sample size. This is how big the sample we obtain in order to get that sample mean. And so now again, looking at the sample mean, but keep in mind that this is only one sample mean we have had. But looking at this sample mean here, then we already noticed that the sample mean itself showed a value much higher than the value being claimed in the null hypothesis. And that is part of the reason leading to coming up with the alternative hypothesis, stating that it's suggested that generally the mean pulse rate of human beings should be above 65. And so now, as soon as we're looking at our sample, then again I must emphasize for anyone viewing the video lesson here that once we can pick up a sample, provided that we have a known sample size here. So our sample that we're having here is at this particular given sample size being 74 people in our sample. But once we're in a known given sample size, this sample mean value that we have is not the only sample mean value. There are indeed infinitely many other sample mean values out there at the same sample size given here. And so, in other words, our sample mean value that we have here is only one among infinitely many other sample mean values at this given sample size. And so that means that we can assign a random variable capital X bar with a subscript 74 to represent the mean pulse rate. The mean pulse rate of a sample of 74 people. That means we don't only have one sample of 74 people. We can have infinitely many sample samples of 74 people. And each one of those give us a sample mean value. And so all sample mean values at this sample size here is assigned to a random variable named capital X bar 74. We learned this idea back in the days that we were studying about the sampling distribution of a mean value. Now with a random variable defined right here, we can have infinitely many sample mean values at the given sample size here. Then we can find the mu X bar, which represents the population mean of all sample means, or in other words, this is the center of all sample mean values. This is the average of all sample means values, in which our sample mean is one among them. And in that way, from this center of all sample mean values, average spreading can also be found. So we learned from the central limit theorem that according to the central limit theorem, the mu X bar is known to be mu, and sigma X bar the average spreading, because once we know the center, every sample mean, including ours, makes some difference away from the center here. Then average spreading is what the standard deviation of all sample mean values is for. And so average spreading, or standard deviation of sample means, is calculated by sigma divided by square root of the sample size that we're given. So that is just a quick reminder about how we can apply our central limit theorem in this kind of problem. And so now, here's my first logical argument right here. The point now is that we are testing to see whether or not this null hypothesis is true. So we're starting out by saying, what if H sub 0, the null hypothesis, was accepted to be the truthful statement? So what if H sub 0 was true? And so now, if H sub 0 was true, then consequently, as I just mentioned a moment ago, that mu X bar must always equal to mu, the actual population mean, according to the central limit theorem. The central limit theorem is guaranteeing this result. However, in this case right here, since we are currently accepting that mu equals 0.65, then consequently, that's what my big head arrow is for. Consequently, mu X bar would equal to 65. And further, as a further consequence, according to the central limit theorem, now back on the wording of the problem, the wording says pulse rates generally have a known standard deviation of 4 beats per minute. So this known standard deviation of 4 beats per minute right here is, in other words, our given sigma value, because think about how it was given right here. Then the description about the sample and the question of our problem here is even written after this information regarding the standard deviation was given. And so regardless of having this information or not, this can be regarded as our population standard deviation because it's completely independent with the sampling information. And so now back on my writing board, according to the central limit theorem, sigma X bar can be calculated by sigma divided by square root of n. But then sigma was given to be 4, and square root of n, we are currently using the sample size being as large as 74 people. So now I am going to substitute 74 into my square root expression. And so, unless being specified otherwise, usually sigma X bar, I'm using 2 decimal places. And so here we're looking at sigma X bar being 0.46. But now the impact of the two lines here is saying that once we have accepted that h sub 0 was true, and for now it's only something that we accepted, keep that in mind. So once we have accepted that if h sub 0 was true, then consequently we would know that this value 65, it was once being as only a claim, but now we can use that as the center of all sample mean values. And at the current sample size we're using, then consequently average spreading, that's what this value is for, average spreading of all sample mean values, spread it away from this center over here, would be on average 0.46. So we found the center and the average spreading. Or in other words, this value is the standard deviation, the population standard deviation of all sample mean values. And now, further addressing the problem, then now once we realize that our sample that we're currently using, and that's the only sample, but that sample is only one among infinitely many other samples. And now at this point, once we found the mean, the average, the center of all sample mean values, as well as the average spreading, or I can also call that the standard deviation of all sample mean values, then for our particular sample mean value, we can find a z-score. So from where our sample mean value is, as one value among infinitely many other values, 73.65, I am going to subtract the mean, or the center of all sample mean values, and divide that difference by the standard deviation, 0.46. This is the standard deviation of all sample mean values. And so this work right here is getting us the z-score. But so this z-score is specifically for our sample. So I optionally use this symbol z-score with a subscript x bar to indicate that this is a not only any z-score, but it's the z-score for our particular sample that we're using here, relative to the center we have consequently found based on the acceptance of the claim value. And with this found average spreading, if we accepted this as the truth, and we are currently using this sample size. And so again, unless being specified otherwise, any z-score is rounded to 2 decimal places. So here I would go with my z-score finally concluded in the final calculation to be positive 18.8. And with a calculation like this, and then I have no choice other than writing that as just only 1 decimal place, 18.8. But that is the z-score indicating how far my sample stands relative to the center of all sample mean values, if that claim was accepted. Now, in addition, aside from knowing the z-score of our sample itself, calculated value being 73.65 and at sample size being 74. But this sample size here was taken from a population where, now let's look back at the computer screen we're having here, but what I'm trying to point out now is that the sample that we found here was taken from a population where we did not know whether or not our population in the beginning was a normally distributed population or not, because the wording in the beginning description of example 1 was only saying that pose rates, plural here, pose rates generally have a known standard deviation. So we have a known standard deviation, but that was it. We did not know whether or not individual pose rates were on a bell curve or not. But now, no worries, because we've learned from the central limit theorem that since our sample size is being as large as 74, our sample size being 74 is now well above 30. And so with our sample size taken to be a value well above 30, then that means our sample size here passes that requirement for the random variable capital X bar 74 to be on a bell curve. So now, in other words, what I'm saying now is that once we have our sample at a sample size above 30, then all sample mean values at this sample size, all of them together, will be normally distributed. So now we know that all sample means of this kind at sample size 74 over here would be on a bell curve data. And so consequently, the center of this bell curve, it's now going to be known to be a bell curve data. Left and right on this line right here would be a value of our random variable capital X bar 74. But now the center of this bell curve would consequently be that value we accepted from the claim in our null hypothesis, being 65. So 65 now would be right in the center of our bell curve. And further, average spreading on this bell curve would be that sigma we have calculated previously. And so that means our sigma value here is going to be 0.46. So as a recap, now with the sample size that we use, with our sample size we use here being 74, then we can conclude that all sample mean values at this sample size here will be normally distributed. And so I'm saying that capital X bar 74 is normally distributed, being placed on a bell curve, can be all distributed by a bell curve data with center at 65 and the average spread being the sigma X bar value we calculated previously, 0.46. And so now, knowing that our sample mean is somewhere on this bell curve, it is beneficial that when it came to the step where we calculated the p-value, in here I have not explained how and why the p-value was calculated as the setup we have seen in the steps, but when it came down to the calculation of the p-value, the setting up was among all sample mean values, we were looking for a sample mean at size 74 to be greater than or equals 73.65. Then my point is now, once we know that our distribution of all sample mean values is on a bell curve, then this calculation of the probability or the calculation of our p-value here can be done as a bell curve problem, where now we can just simply think of a bell curve, center at 0.65, just as drawn here in the picture, but now 73.65 is somewhere to the right hand side of the bell curve, and then that probability setup here is to be calculated as an area, as the area on this bell curve shaded to the right hand side of 73.65. And so in that way, that's how I entirely proceeded on with this calculation of the p-value, by saying that this area on this bell curve here would equal to the area on a standard normal, on the standard normal distribution bell curve, where z-score, we were looking for z-score greater than or equal to positive 18.8. And there, at that point, once we made the connection between our bell curve here with the standard normal distribution bell curve, then the answer coming out from this is simply just 1 subtract the answer from the LS&D program at z-score, given z-score 18.8. And so, of course, the answer there we regarded as the p-value was 0.0000, indicating that it's a value very small, not absolutely 0, but very close to 0, very small, so that in 4 decimal places it's all just 0. All right, so let's look again at the bell curve a little more carefully. We've learned a while ago that in any data set, in any data, those values having z-score inside of the interval from -2 to 2 are being regarded as the usual values. And so, of course, those values that having z-score either above 2 or below -2, indicating being 2 standard deviations above mean, or 2 standard deviations below mean, those values are being referred to as the unusual values. And the reason for this is that according to the empirical rules on a bell curve, a normal distribution, where mean value is always known to be right in the middle of the bell curve, then there are about, we've learned from the empirical rules, and here since we don't need to pull out a calculator and do formal calculation, and so empirically speaking, there are about 95% of data being located inside of the interval anywhere from -2 to 2 for z-score, the interval of from 2 standard deviations below mean to 2 standard deviations above mean. And so in that way, according to the empirical rules, then there's only 5%, there's only 5% of area on the bell curve being outside, and that area is being equally distributed on the 2 little tail here. That means now if I'm making a shading, this little tail is only a 2.5%. There's only a 2.5% of those values being above z-score 2, or there's only a 2.5% of those values falling below z-score -2. And having low probability like that, low percentage like that, that's why they are those values being referred to as the unusual values. Now, noticing how the area of all the usual values are being located right in the middle as a big fat area in the middle of the bell curve, and the area, the 2 areas where the unusual values are being located in the 2 sided tails, 2 squeezed tails on the bell curve right here, to the left and to the right. Then we can extend that concept further to a generality on the bell curve. That now, generally on any bell curve, with the mean right in the middle, then we can always have, there's always a big fat area in the middle. And now in this generality, I refer to the big fat area as the common area. It's the common area, or this area is where we have all the common values. So all the values in here are referred to as common values. Okay, as the terminologies. And outside, equivalent to these 2, the outside areas, then outside of the common area now, we can refer to these 2 either to the left, that area extremely to the left, or that area to the right hand side here in the tail. We can refer to these as, the values in here are the unlikely value, because due to the fact that they are located in the areas where it is very low probability to be in there. So any value has low probability to be in either the extreme end on the left or to be in the extreme end on the right end. And so these unlikely values are at low probabilities. And the area itself, we refer to them as the unlikely area, where we have unlikely values. And now, relating to the empirical rule that we just briefly recall, then 2.5 being considered as a low probability is only to a good majority of people out there. But then, for some other people, a probability being 2.5 is still not small enough to be considered as unusual or unlikely values. And so, in a general idea here, then the area, the unlikely area here, each one of the unlikely area here can be even smaller than 2.5% to be regarded as the unlikely values, indicating that or being low probability. And so that's why in our problem of testing a hypothesis, then significance level notated as the alpha symbol can sometimes be even given smaller than these commonly used value 2.5% and 2.5%. But significance level, now in this concept of being the common area or the unlikely area, then the significance level in a testing hypothesis problem is how much area being to the right outside of the common area value, or how much unlikely area being to the left outside of the common area values. The significance level is in other words, the probability of how low the probability that a value can possibly fall into this unlikely area or fall into the left side unlikely area. And now, specifically in our testing hypothesis problem in example 1, part A. Looking at our computer screen here, we have a significance level given to be 0.01. So our alpha equals 0.01 or 1%. But that means this right tail, the little tail outside of our common area value right here. So this right tail is being as big as 0.01. And the very same significance level being 0.01 in our problem means this left tail, the unlikely area, the area outside of common area, but being to the left of the bell curve, is also 0.01. So in other words, significance level is a way to indicate how big the amount of area, the amount of unlikely area outside of the common area. All right, so now back on the bell curve that represents our distribution of all sample mean values. So again, this is the bell curve where any value on this line is a sample mean at size 74. We have learned how the value being claimed in the null hypothesis has become the center of our bell curve for representing the distribution of all sample mean values at size 74. So consequently, 65 is right in the middle of this bell curve. And then we have seen from earlier explanations that this bell curve has a common area. The common area big fat in the middle here is being as large as 98% common area. And that was due to the fact that the significance level given in the problem was only 0.01 or 0.01 or 1% on each little tail. So alpha equals 1% here and alpha equals 0.01 or 1% here on the left hand side. So that's what we already learned from the earlier explanation. And so now our sample mean value that we have found, x bar, we found our sample mean value being 73.65. So now this sample mean is clearly greater value than the value being claimed at the center. Or in other words, this sample mean that we have found is clearly to the right hand side of the center of our bell curve here in this picture. However, we would like to find out, we're interested in finding out whether this sample is high enough, is to the right hand side of 65 of course, but far enough so that it would fall into this 1% unlikely area to the right hand side. So recall again that we call this red area, it's the significance level given, but we refer to that as the unlikely area. And in our case here, since the sample already known to be to the right hand side of our center of the bell curve of our claim value from the null hypothesis statement, we are further interested in finding out whether this sample would any possibility fall into the unlikely area to the right hand side of the common area. I will give the explanation why we're interested in finding out whether our sample would fall into the unlikely area to the right hand side of the common area in the later steps, after we finish putting all the pieces together, after we finish putting all the details together. But for now, that's what our plan is. We would, again, from where this sample mean value is already known to be to the right hand side of the value being claimed in the null hypothesis, we are interested in finding out whether this sample would further fall into that tail, that red unlikely area to the right hand side of the common area. And so because that's what we're particularly testing, we're testing to see if our sample we have found here would fall into this unlikely area on the right hand side of the common area. And notice how this unlikely area to the right hand side of the common area appear to be a tail, a little weeny tail to the right hand side of the common area. That's why this kind of test we're doing is being referred to as the right tail test. And so generally speaking, a right tail test means anytime we found a sample and we already found out that our sample appears to the right hand side of the value being claimed in the null hypothesis, and we would like to further determine if our sample there would even fall further into the little tail to the right hand side, the unlikely tail to the right hand side of the common area. That's what a right tail test is. And so now recall from our steps being displayed that the p-value was calculated to be 0.0000. And this p-value itself, as a calculation setup, it was p-value to be equal to the probability that among all sample means at size 74, we want to find the probability that a sample means would be greater than or equal 73.65. So that means correspondingly on the picture of our bell curve, This calculation setup of the probability is graphically represented as .65 is in the middle, and 73.65 is somewhere already knew to be to the right-hand side of the bell curve center. And again, what I was in the middle of saying was that this probability is graphically represented as the area shaded to the right-hand side from where our sample is. And so now connecting with the p-value, then this area shaded to the right-hand side of our sample mean value, and being shaded in black here, is the p-value. So this is on the right tail, little right tail, this is how big our p-value is. And then further, we made the comparison that p-value is being less than the significance level, 0.01. This is just simply a direct comparison. Once we've calculated our p-value, we just simply compare that with our given significance level, and apparently our p-value was smaller. Again, on this bell curve, the black area being shaded to the right-hand side of our sample is graphically the meaning of the p-value. But now 0.01 is the amount of unlikely area to the outside of the common area to the right tail. And since p-value is being smaller than the significance level, that means if I would draw and if I would blend in the right tail area, the right tail unlikely area on this bell curve, then the picture would look like this. Black shaded area is here, but the red area must be here, because the red area is obviously right out from direct comparison is larger than the p-value that we found, or the p-value we found is smaller than the significance level represented by the red. And so, or another way of seeing, graphically speaking, the black area is being completely contained inside the red area if we're blending the two areas together. And so now that is clear enough to see that in this way, once we have compared our calculated p-value with the significance level, then it is now sufficient to say that our sample mean we have found here is, see, so now it must be clear that our sample mean must be falling inside of the unlikely area being in red there. And so now the first thing we can say now is our sample mean is among the unlikely values, because the unlikely values are all made up by that red area. And now the black shaded area here is completely contained inside. So now one thing we know for sure, the X bar, our sample, is where it starts. It's where the black area starts. It's contained completely inside of the red area. So X bar must be among the unlikely values. And so further, we can even say that now X bar itself is an unlikely value. Now that we know our sample mean value, X bar, is among the unlikely values, leading to X bar itself, our sample mean value, is an unlikely sample value itself. Specifically, it's an unlikely sample mean value. Now I am going to explain why, because we have seen earlier in the steps that once we can prove that our sample value is an unlikely sample value, it leads to the sample itself is a strong evidence. So now I'm going to explain why our X bar being an unlikely sample value leads to itself being strong evidence or showing strong evidence. For us to reject the null hypothesis H sub 0 or to support the alternative hypothesis H1. Now again, let's put ourselves back on that bell curve representing the distribution of all sample mean values at size 74. And so that means on my bell curve here, any value found on this horizontal line is a value to the random variable capital X bar 74. According to our null hypothesis, H sub 0, stating that or claiming that mu, the population mean value of pulse rate, is equal 65. If we accepted H sub 0 to be true, so recall that we had this line earlier in our reasoning that if H sub 0 was accepted as a true statement, okay, so if H sub 0 was accepted as the true statement, then consequently this mu value would be the center of our bell curve here. This bell curve, according to the central limit theorem, would take the value claimed in our null hypothesis here as the center, because recall for yourself, mu x bar, which is the center of this bell curve, is always equal to mu, and mu in our case here is accepted to be 65. And so consequently, our bell curve here representing the distribution of all sample mean values at size 74 has the center right at 65. And so being a bell curve here, just like any other bell curve, has a common area, big fat area in the middle, right around the center. And outside of that common area, there's the unlikely areas, two unlikely areas. One is to the right tail of this bell curve, and one is to the left tail of this bell curve, and both unlikely areas are being shaded in red ink. And so from what we've learned previously, the significance level given in our problem is indicating that this right tail area being shaded in red right here, or we regard to that as the unlikely area, is only as large, as big as 0.01, or as a percentage, it means it's a 1%. Then the same way would be for the left tail here. According to our given significance level, it would be another 0.01 amount of red area shaded, but to the left of the common area, outside of the common area on the left tail. And that is again equivalent to or equal to, in percentage, a 1% amount of area. And so now quickly doing the math, we can see that our common area here in the middle, again remind yourself the way of any bell curve, total accumulated area inside any bell curve is a 100%, or 1. Then after taking away the two tail areas here, which summed up to be a 2%, then there must be 98% of area in the middle here, in that middle big fat area where we call that our common area. And now I'm about to explain how this 98% being that big in our common area impacts our decision about how our sample value was concluded to be a strong evidence. So this is how we are going to understand about the 98% common area. Anyone testing a hypothesis must understand that once a claim is made, or once we have the center of a bell curve, then any sample mean that we pick up is expected to be different, is expected to differ from the center, from the center in the middle of the bell curve. It's just the way it is. Or in other words, any sample that we picked up can make some difference with our center from right in the middle here. Either only a small amount of difference or a large amount of difference. And so this 98% in the common area means we accept 98% of those values that fluctuate from the center. And I use the term fluctuate, means some value can be a little bit above, or some value, sample value, can be a little bit below. But we will accept 98% of those values fluctuated away from this claim in the center, and regard to those as values that we commonly see. So again, the 98% common area here means there are 98% of those values that we regard as values that commonly fluctuated away from this center. So the idea now is that if the sample mean we found, of course we have to accept some certain amount of fluctuation. But so if the sample is found to be inside of the common area, then we will accept that and we will regard to that sample as, yes, it's just some amount of error that's commonly seen, because nobody is perfect. Nobody can make a claim where it's exactly the truth. So we must accept some amount of fluctuation. So again, if the sample falls within the 98% common area here, then that means we can accept that sample and nothing's wrong with the claim. But what if the sample mean is far enough to the point where it's either falling into the right tail unlikely area there, or it's far enough lower than the center so that it would fall into the left tail red shaded area there, either one of the two unlikely area. So the plan now is that once we can successfully prove that our sample falls into either the right tail unlikely area or the left tail unlikely area, that's indicating that it's very unlikely to have the sample like we have here in the way how the claim was accepted. What matters is all about whether the difference, the fluctuation from our sample to the center can be accepted or being unacceptable due to the fact that it's so unlikely to fall into these areas. And so another way of arguing this is that, so in that way, as I have explained, then we accept up to 98% of values that fluctuate away from the center to be regarded as the commonly fluctuated values. Then, and being such a large percentage, that means yes, we are okay with sample being different from the claim, but any sample, even though being different from the claim, any sample mean x bar here, right at the instant that we're picking it up and before we even know the value of it, any sample is expected to be in the common area because it's so big. 98% is really close to almost the entire bell curve. So any x bar sample mean value is expected to be in the common area because due to the fact that we accept such a high percentage of those values being regarded as commonly fluctuating away from the center. And now I have to open a parentheses and make a little note here. See, at 98% chance. So 98% chance we should expect that any sample we picked is being inside of this common area. But now our x bar sample mean value being at value 73.65. Yes, it's to the right hand side of 65. It fluctuated from 65, but it fluctuated too far to the point that our value is proven, is immediately, I would say immediately, due to the fact that it's the only one sample, and we immediately can prove that this sample fell right into the unlikely area, or in other words, our sample mean 73.65 is immediately a or an unlikely value. The chance of getting a sample mean like this is only a 0.01 chance, or only 1% of time that we get a sample like this. But why is it that our only one sample ever, and we immediately can calculate that it falls right into the unlikely area and making it an unlikely value? And that is the reason why, that is how it's contradicting, because if this statement was the truth, again, recall for yourself that h sub 0 was saying mu equals 65. And consequently, we said if we accept h sub 0 as the truth, if h sub 0 was true, then consequently 98% of time I am expecting x bar that we found to be inside of this common area, where we regard to those as values that are commonly fluctuating away from the claim. Of course, we have to forgive the person due to a little bit of fluctuation in the value where his claim is and the value we have. But here our sample did not stay in the area where we can accept. It fell right into the area where the calculation showed that it's very unlikely to reach a sample like this. But it's there, it's already there in our hand. And so in that way, this is the reason why it leads to saying that our sample is a strong evidence. Because of its very unlikely nature right there. It leads to its being strong evidence. And for what? Strong evidence for us to say that we are going to reject h sub 0. Or we can say x bar can be used as strong evidence for us to support the alternative hypothesis, suggesting that mu should be greater than 65. And now let me clarify a little further about the idea of formulating the alternative hypothesis. So now that we have had our null hypothesis, in this particular problem, the claim was stating that mean pulse rate was to equal 65. And if this claim was true, we use that as a value claim in our null hypothesis. And so if that claim was true, we have seen throughout a lot of our explanations previously that the claim there, if we accepted that, if h sub 0 was true, then this value in the claim, the value being claimed in the null hypothesis consequently became the center on the bell curve, being 65 at the center. And then in that way, again, with the common area being as big as 98%, and I should have said, even though for the common area on this bell curve representing the distribution of all sample mean values at site 74, and even though the common area on that bell curve there is being as big as 98%, our sample mean that we found being 73.65 still did not stand at all anywhere inside of the big common area here, but instead our mean value, our sample mean value fell right into the unlikely area to the right hand side, and that was making this sample mean value that we've had right here as a strong evidence to reject the null hypothesis, claiming that the mean value, population mean value of pose rate equals 65. So another way of understanding this now is that rejecting this value here means the claim being stated in the null hypothesis here is a little too low. So think about the person who made the claim now. And another thing to realize, a sample is a sample. Once we picked up a sample, that is a reality that we can use. We can never change the value, whatever that happens in our sample, unless we change to a different sample. But even if with a different sample, a sample is a sample. We cannot change whatever value that came out from that. So right here from our only sample that we have found, think about the person who made the claim in the null hypothesis, claiming that mu representing the mean pose rate to equal 65 right there. If that person would claim a value for mean that's somewhere higher than 65. So now I'm starting to go a little abstract here. I'm not specifically pointing to any specific value to be higher than 65. But what I'm saying here is that if that person originally was making a claim where claiming a value being anywhere above 65, then think about it. That claim there could have been a value above 65 and high enough so that once it became the center, and of course the center of this sampling distribution now should be above 65. But once that claim there is changed to a value anywhere higher than 65, then this big common area is going to be shifted along with that. So think about when it was 65 being in the claim, then the 98% common area is right here. Always common area is right around the value being claimed, now being regarded as the center of the bell curve. And I should have also shaded this left tail area, even though we didn't really use that in our problem. But now what I try to emphasize again now is that even if we bring our claim to a value higher than 65, then the 98% common area would still be there, because any bell curve has a common area being right around the center. And so with this 98% being the common area, and once the person who made that claim changed to a value for the claim being anywhere higher than 0.65, then the first thing to realize is that common area would shift along with that to always maintain being around the new center. And so the idea now is that, and there will always be the two unlikely area values as the two little tails outside of the common area. And so if the person who originally made this claim made a claim anywhere higher than 0.65 and higher enough so that our sample, wherever it stands, and notice on this line of values, we can change the center of the bell curve to a different value, but where the actual sample mean value stays, where our actual 73.65, because as I said earlier, once we found this value, it will never be changed, and it takes its own place on the line. So here, when the claim was 65, then that made our sample mean stand right in there inside of the red area, unlikely area to the right hand side. But who knows, if the person who made the claim can change the value in the claim to be anywhere higher than 65 and high enough so that this claim now would be a sample point that belongs somewhere inside of this 98% common area. Or in another way of saying, if the claim is shifted to the right high enough so that the common area would now contain the sample mean value inside of it, then this sample mean would no longer be an unlikely sample. So if x bar stays inside of the common area, then that means it leads to saying that x bar is a common value. It's a common value. And in the way how I see about common value means this sample is just like any other sample, being among those sample values that commonly fluctuate away from the claim that was made. And like I said again, this is after the person can change to a higher claim value, anywhere higher than 65, so that our sample mean would fall inside of the common area. And now in that way, again, compare with the claim, then this sample mean would become a sample mean where it's just being regarded as a common value, and common means it's just any of those values that are regarded as commonly seen fluctuating away from the center. And so in that way now, making x bar being a common value, then that means x bar is no longer strong evidence. Or in other words, to be straightforward, x bar is, if x bar is inside a common value, then x bar is not strong evidence. It's not providing strong evidence. Because we can accept that. We can accept that because it's still among those values that commonly fluctuate away from the center. And we have to be able to forgive the person who made the claim, even though it's already above 65, but maybe not exactly be the truth, but our values is being a little bit different, but still being commonly being referred as those values that commonly differ from the actual mean. So nothing's wrong with that claim there. And so that's why x bar is regarded as not strong evidence. And that's the whole idea about suggesting an alternative hypothesis, or saying that an alternative hypothesis, symbolically H1, is the statement that suggests, hey, if H sub 0 claiming that mean pose rate equals 65 was a little too low, then suggesting that mean pose rate is a value anywhere above 65 and above far enough so that this x bar would become a common value, then that's where it could be accepted. And that's the whole idea of coming up with the alternative hypothesis.